Alright, so we're going to look at what we need to do to estimate the variance of a population given the data that we have. And what we're going to end up using is something called chi-squared. And so we can estimate the standard deviation of a population using, the variance of a population using the variance of the sample, or we can estimate the standard deviation using the standard deviation of the sample. But because standard deviations are dealing with something that's already spread out along a normal, when we look at how these play between the sample and the population, the distribution is mathematically, for lack of a better word, really ugly. And what we're going to do is we're going to talk about a thing called chi-squared. Now, chi is a Greek letter. It looks like this. And the calculation for it is like this. And so we can use chi-squared as part of designing our confidence intervals as we try to make good guesses at what the variance of our population will be using estimates. And so this is what chi-squared does. Now chi-squared develops a set of curves, and they're skewed right. The area under the curve is 1. No value is greater than 1, and no value all the values are greater than or equal to 0. Sorry, their value and the total area is equal to 1. And they're based off of degrees of freedom, so different degrees of freedom create different chi-squareds. Let me pull up a graph of one here, and I'm not going to try to draw it here, so give me 1 second. Oops, here we go. That's not, that is a table of chi-squareds, but let's get a actual chi-squared function here for you. I think that's it. There we go. And so these are what all the different chi-squareds look like. And if we notice, getting near 30 degrees of freedom, it starts to look normal. But it is definitely skewed on the positive side. And as there's smaller degrees of freedom, it has a very large spike. And so here's 5 degrees of freedom, spikes here and comes across. 10 degrees of freedom, spikes here and comes across. 15, and then 30. And so it's known for these really large tails in the distribution, which means the values won't be symmetric. When we were using critical values before, they were symmetric. And what I mean by that is when you found your Z critical, you got a negative value for it. And so you could have your left and your right sides found for you. But in chi-squared, you can have a left and a right side that are non-symmetric in their values, where their values come across based off of the proportion that we're looking through here. And so we kind of have to look at the left and the right side as separate entities as we build this. Luckily, our technology does a great job of it for us. And so, but let's look at this. I think I'll do, again, this is a drawing issue here. There are 2 critical values. Notice it's a chi-squared right value, and that's 1 minus the critical value divided by 2 gives you the area on that side of it. And then to find the left side, we actually calculate the area of this whole thing and subtract 1 from it, because we want the complement, the gray part. And that'll give us the area for the left chi-squared, which is 1 minus the critical value over 2. And that will give us the 2 critical values, the left critical value and the right critical value. But the thing to note with these is that, they're not symmetric. So let's pull up how they look here. We put them all together. 1 minus c divided by 2 gives me this bit. 1 minus c divided by 2 gives me this bit. But because it's a backwards reading table, we have to do the extra 1 minus to get this part here. Right? And so we come back and look here. Right? Because this table reads the percentage in the blue and gives us the critical value. To get this gray bit, we need to 1 minus c over 2 to get that. And that's the thing we've been doing with complements. But let's actually get a critical value, both left and right, and we'll do that in our technology here. Let's see if I can get my technology open on. There we go. I have 2 critical values here, and notice how different these 2 values are. They're going to be positive values coming across, and we'll show how we can do this with technology to make it easier for us. So what I did here is this is my left value. And Excel has a built-in function for chi-squared to get the critical values. And so notice this weird command, chi inverse, chi inverse. If I say chi, it's not a T. CHIINV. And then in the confidence value I was looking for, the C value. And then in my degrees of freedom. And that gives me the left chi-squared. Let me actually put that in here for you. F left. I'll actually do this is chi-squared left. And this is chi-squared right. And now to get the right value, I have to do the 1 minus the C value. And that works it for us. And that we're able to get the critical values that come out of chi-squared. And so this is probably the best way to do it. Your calculators have chi-squared functions on them. There's chi-squared distributions you can use. We really want the inverse. We want the critical values that come out of it. And let's use the critical values now that we can calculate them. And so what we want to do is we want a confidence interval for the variance. And so the confidence interval for the variance has n minus 1 times my sample variance, right, over the right chi-squared value. And that's going to be less than or equal to my population variance, or less than. And then in the left, or the upper value, has my left in it. Notice these are backwards from how you would say them, right? This is the left side of my inequality. This is the right side of my inequality. But the chi-squared critical values are alternated there. And that's how we find the estimate for the variance, which then for the standard deviation, since the standard deviation is the square root for that, we take the square roots. Now remember, this is going to be a number that comes out of your formulae. And this is going to be a measure you have, and this will be a calculation. And so you'll see in next week, Wednesday's project, you'll calculate these completely for your parking ticket data, because now you can use your parking ticket data as a sample, and we can actually talk about our confidence of what is the mean. plus or minus error. And what is the standard deviation? Plus or minus error on that, because we have the tools to do it now. And we can even talk about what percent of the tickets, and what is the percent estimator, are $30. Right? These are all things we can talk about the parking ticket data, because we now have confidence intervals to do it with. But let's use our chi-squared confidence interval equation here to find one. So let's see here. Want to get to the data we were using there. So if we have a normally distributed population, let's get our estimates. Here we go. Let's use this one here. So what we have here is we're selecting 30 samples of an allergy medicine, and the sample standard deviation is 1.2 milligrams. Assuming the weights are normally distributed, we want a 99% confidence interval for the population standard deviation. And so let's pull our key values over into our workspace here. Erase this and we'll get our key values into here. And so from that we have taken 30 samples. So our n equals 30. And our sample standard deviation is 1.2 milligrams. And we want to estimate at a 99% confidence our population standard deviation. So to do that, we are going to need to find our chi left squared and our chi right squared at a 0.99. With, now our degrees of freedom are always n minus 1, or 29 degrees of freedom. And I'm going to use technology to do this for us here, so that we can work our way through this. So let's get over to our technology here. And so since I left these in here, I have my left chi-squared. Well, I need to change my confidence value to be 99 and my degrees of freedom to be 29. And that gives me a 14.256 as my left chi-squared. Am I missing anything here? Oh, yeah. I have to divide by 2, right? So if we look at my C value, it's C divided by 2. What I need is 0.95. And let me show you that, because this is something that I have to double check all the time. Is if I want a, let's come back here. If I want my confidence interval on chi-squared to be 99%, so 0.99 is going to be in here, then 0.05 is here, and 0.05 is here. So the value I put in for my calculation is 0.99 is 1 minus that 0.05, or 0.995. So we want how much is in the shaded area. And over here it's going to be 0.05. But we can get that by subtracting 1 from this. 0.005. Get my extra 0 in there. 1 subtracting for this. And so always remember, because these are always two-tailed, we always need the half value of that. And so you're thinking a 99% confidence, that'll always give you 0.995 as your confidence value. A 95% confidence will give you 0.975, because there's 2.5 above and 2.5 below. 90% confidence is 0.95 because there's 0.5 above and 0.5 below. So these are things to watch for on critical values. I always type it in first, look at the number, and go, wait a minute, I did that wrong, just like I did there. So let's come back here. There's the notes. Here we go. And so what I want to do is I want to take this 0.995 and the 29, and I want to subtract 1 from it. So 95, and my degrees of freedom are 29. And now I have my 2 chi-squared values that I can use to calculate my estimates for my standard deviation. Now what I'm going to do is I'm going to bring some things over in here. So I had n equals 30, and I had a sample standard deviation of 1.2 milligrams. And so what I'm going to do is I'm going to take that entire formula for the upper and lower bounds and make it part of my spreadsheet. So let's look at this formula. So I'm doing the standard deviation, so I'm doing this lower formula here. And notice it has calculations based off of things I have. So I have the standard deviation, not the standard deviation squared, so I can put this all into the computer, and I don't have to carry things back and forth. So I'm going to show you how to do that, locking the cells in place. So the lower bound, the lower limit, well, the formula says that my standard deviation is trapped between the square root, so equal square root. Make sure I'm showing not the okay. And I'm going to put parentheses to put things in the square root, and then parentheses again. And the first thing it needs is n minus 1. Well, n is in cell A5. So I'm just going to put in A5 minus 1. And that's my n minus 1. A5 minus 1. And then I need to multiply that by the standard deviation squared. So I'm going to multiply by, I'm going to fix my cells here because I made a small cell error here. I'm going to make this B5, and we'll fix it in a second. Because what I didn't do is make these numbers. And we'll fix it here. I'll show that fix. And so there's my B5 minus 1 times the standard deviation, which is going to be B6 squared. And then we divide it all by the right chi-squared, which in this case is B2. And we should get an error here because I don't have numbers in here, but I'll quickly, that's 30, and that's 1.2. And there I get my lower limit of my chi-squared, or my standard deviation. Now the upper limit, I'll do the same thing. And so my equation is it's equal to the square root of n, so that's B5 minus 1 times my standard deviation, which is B6 squared, that's what the up caret does, divided by, and now I want my B1. Whoops, I typoed. Where did I typo? B1, let's see, that number's right, the B6 is right. Did I forget a parenthesis? That's copy this one. Ah, I forgot my multiplication sign. Right there. And there we go. B1, let's see here. B1, n minus 1, I have n minus 1, 36 squared, divided by 52. That's right, divided by 13.121. I'm getting a slightly different number than the book here, and yet let me make sure I did not calculate. I calculated that right and calculated that right. N minus 1, B5 minus 1 times. Yes, these are my standard deviations, not my variances. So there we go. We got our standard deviations. Sorry for the mumblings. Chi-squareds are really, I take my time with chi-squareds because this is an odd equation. And so let me come back over to the blackboard here and write this all in. And so my standard deviation of the population for this, based off of what popped out of there, is that the standard deviation is going to be between those two values that popped off the sheet, which is 1.784, so 1.78 on the upper end, and 0.89. Which isn't bad because our estimator, the sample population, was 1.2. And so we have an idea of where our standard deviation for the population is, which, if you remember from our previous problems, helped us decide if we were going to use t-tables or not. And so if we can get good estimators in here, we can begin saying we know what the standard deviation is. And that's how chi-squared is used. It's a messy equation. Take our time and let our technology get us there, and we can get these endpoints for these estimations. Notice these aren't symmetric like the normal curve, and that always throws people off, that the left and the right side are noticeably different.